Okay, continuing here with a look at oxidation numbers. Begin with the intent of doing some evaluating some reactions to identify oxidation reduction, that sort of thing. So the second example here is sulfate, and let me do it the same way that I should this sort of system for doing oxidation numbers versus algebraic charge. So again, I'm putting the oxidation number of the atoms below, the total algebraic sums above. Now, sulfate is a polyatomic ion, so the -2 charge, that's what the oxidation numbers are going to add up to. But again, we kind of want to apply the rules in order. So first thing would be oxygen. Oxygen is -2 here in terms of oxidation number. Because there's 4 oxygens, that would be an algebraic total of -8. Now, whatever the sulfur is, if we subtract 8 from it, it's going to equal -2. That's that 7th rule. Add up to the charge. So that means sulfur here has to be +6. So we'd say the oxidation number of sulfur here is 6. Oxidation number of oxygen is -2. Okay. Dichromate here, similar in that it's a 2- anion, right? What we have to watch out for here, just like when we're doing ionic formulas, is when there's multiple metals, we have to factor that in. So total of -2, oxygen we know starts as -2 because there's a rule about oxygen. 7 of those means algebraic total is -14. Now what that means is from the 2 chromiums we need a total of +12, because +12 minus 14, that would be -2, which is the charge there on this ion. Now, if that +12 is spread over 2 chromiums, though, that means each chromium has a charge of +6. So the chromiums in dichromate have an oxidation number of +6. Okay. NO2 positive, so I threw this one in here just so we have one where the charge is a positive number. That means when these add together, they should add up to +1. But oxygen, again, -2. So that's a total of -4 from oxygen. That means the nitrogen here's got to be +5, because 5 minus 4 would be +1. So the oxidation number of this nitrogen would be +5. Okay. Now, we want to do this in equations as well, and then look at all the pieces of the equation, and particularly comparing atoms on one side to the other side to see if there is a change. So let's look at some reactions. We'll go through, we'll figure out the oxidation numbers, and then we'll identify whether there was an oxidation and reduction, or whether there weren't oxidation and reduction. Right? If all the charges stay the same, all the oxidation numbers stay the same, then that's not an oxidation reduction reaction. Okay, we've got copper 2 chloride here. Now that's an ionic compound. You should be able to work out the charge from the anions, and we know the charge of the anions because of where they are in the periodic table. So charge here would be also oxidation number. So +2 for copper, -1 for the chlorides there. Aluminum in the second spot here on the reactant side, that's the elemental form of aluminum. So that is 0, I think by that first rule. But over here on the product side, aluminum chloride, that is the cationic form of aluminum, so that would be +3. Chloride, though, still -1, because that's still the chloride form of chlorine. Copper on the product side here is in its elemental form, so that is a 0. Right? Now, if you see elements, that's a good indication you are looking at an oxidation reduction reaction, because if they were still elements on the other side, they wouldn't be part of the equation. So what we're looking for here are changes. Copper was +2 and it went to 0, and aluminum was 0 and it went to +3. Right? Now 0 to +3 is getting more positive. If you're getting more positive, that means you're losing electrons. So aluminum lost, and I'm going to do it by each aluminum here. Each aluminum lost 3 electrons here in this process. But losing electrons, that is reduction. Right? Remember, no, that's oxidation. Remember, Leo the lion says Gur. Leo, loss of electrons, is oxidation. So we would describe the aluminum here as the oxidation in this reaction, or being oxidized. Copper was +2, and it ended up at 0, and that means it is heading towards negative charges. From positive to 0 is on the direction to negative. That means it's gaining electrons, and gaining is reduction. So each copper gained 2 electrons here, and that's reduction. And another thing we could look at is the number of electrons lost and gained should be the same, right? The stoichiometry of the reaction plays a role here as well. We said each aluminum lost 3, and there's 2 aluminum, so that's 6 total electrons lost. Each copper gained 2, and there's 3 coppers on each side of the equation. So 6 electrons were lost, 6 were gained, but that should balance out in your equation. So that is an oxidation-reduction reaction. Aluminum was oxidized, copper was reduced. So I think the best way to say it is to pick out the atom from the molecule and say the copper was reduced. Because notice the chloride, nothing happened in terms of electrons with the chloride. It had a -1 oxidation number on the reactant side, still -1 on the product side. It wasn't oxidized, it wasn't reduced, it stayed the same in terms of oxidation number. Okay, next example, right? Same thing. We just want to go through, find all the oxidation numbers, and then evaluate them. Elemental form of copper, that would be 0. Right? Now nitrate, here's a polyatomic ion. We've got to apply our rules. So the first rule to apply would be oxygen. Oxygen is -2, but 3 oxygens in here. Again, I'm going to keep the algebraic sum on the top, and I'm indicating the oxidation numbers underneath. That's a good way to do it. Right? If you do it a different way, let's say on an exam, make sure you make it clear to me what you're doing, because if I have to interpret it, then you didn't really provide a clear answer like you should. So -6, we're looking for a total of -1 because of the charge of that anion, and there's only 1 nitrogen. So that means the nitrogen's got to be +5 here in this case, because +5 minus 6 would equal -1. H3O plus, that's hydronium ion. That's something we'll encounter quite a bit when we start talking more about acids and bases, particularly in aqueous solutions. But if oxygen is -2 and hydrogen is +1, those are both separate rules, that accounts for the +1 charge on hydronium, because we have 3 positive charges and 2 negative charges, so a total of +1. So we really don't have to figure anybody out there, they just follow their rules. Now on the product side, copper cation, that's got an oxidation number of +2, just like its charge. Right? N2O, again, oxygen's -2, 2 of them, that's a total of -4. That means this nitrogen is +4. And then water. And water fits right into the described charges for hydrogen and oxygen as well. +1 for hydrogen, there's 2 of them, -2 for oxygen. Okay, so now we can identify the changes. Let me go with the color coding here. Copper went from 0 to +2. Right, so if it's getting more positive, that means it is losing the electrons, losing the negatively charged particles. So this is losing electrons. That, of course, is oxidation. Losing electrons is oxidation from Leo. Right? And then the other one, another color here, is the nitrogen. Nitrogen starts off at +5. Over here on the product side, it ends up as +4. So it is becoming less positive. That would correspond with gaining an electron. So gaining an electron, that is the reduction. So the copper is oxidized while the nitrogen is reduced in that reaction. Okay, and one more example here. I think we can squeeze it into this video. Fe2O3, that's iron 3 oxide. That would be iron 3, and oxygen is -2. That's just an ionic compound. Carbon monoxide, we'd apply the oxygen rule. Oxygen gets to be -2. That means the carbon here has to be +2, because we need an algebraic sum of 0. On the product side, iron is 0. And then 3, carbon dioxide. Again, we'd start with oxygen getting to be -2. That's an algebraic sum of -4. That means this carbon is now +4. So there's our changes. Iron went from +3 to 0, and carbon went from +2 to +4. So +3 to 0, that is headed in the direction of negative. That means iron is gaining electrons there, and gaining electrons is reduction. So the iron is being reduced. +2 to +4, that means you had to have lost the negatively charged particles, so that now there are more of the positively charged particles in the nucleus left over. Losing electrons, that is oxidation. So the carbon atom in the carbon monoxide was oxidized in the course of this reaction. The iron from the iron 3 oxide was reduced. Okay, there's a few more practice problems in the lecture notes. We'll handle those in one more video, but we'll call an end to this one